On a clear autumn night in the northern hemisphere, if you walk far enough from the sodium yellow glare of city lights and let your eyes adapt to the quiet of the dark, you can lift your gaze above the jagged silhouettes of trees and rooftops and notice, above the familiar band of Cassiopeia's bright W and the crooked rectangle of Pegasus, something that almost doesn't look like anything at all. A faint, elongated smudge, a thumbprint of light barely pressing into the black. It is easy to miss, easy to dismiss as some trick of your vision, but that soft haze, larger in apparent size than the full moon, yet so diffuse that it hides from casual sight, is the Andromeda Galaxy, the most distant object you can see with your naked eye, whose light left its stars when no human being had yet dreamed that those stars were not part of our own cosmic home, when our entire understanding of the universe fit comfortably inside what we now know is only one spiral among billions, long before anyone spoke the word galaxy in its modern sense. That pale mist was woven into human stories as firmly as any legend carved into stone. For the ancient Greeks, the patch of sky in which his manuscript illustrations show a small elliptical blur roughly where we would place the Andromeda Galaxy today. And though we had no notion of its colossal distance or of individual suns bound together in a gravitational dance, that quiet note, little cloud, is the first unambiguous historical record we have of someone writing down that they saw the light of another galaxy. In China and Japan, where imperial astronomers kept watch for omens on the sky's great scroll, the region of Andromeda was divided differently, mapped into their own asterisms and lodges, and although their surviving catalogues from the same era focus more on transient phenomena, guest stars, comets, eclipses, than on faint permanent smudges, later records would show that East Asian observers too became aware of a hazy patch in that part of the sky, perhaps independently, perhaps through the slow exchange of knowledge along Silk Road routes that carried not only silk and spices, but also star lore scribbled in different scripts. Yet in each culture the mist remained a curiosity, an object to be noted, not yet interrogated, an entry on a list, rather than a door to a larger universe. When the telescope arrived in the early 17th century, first as a crude spyglass in Dutch hands, and then as a sharpened instrument in the grip of Galileo, the sky that had seemed smooth to the human eye suddenly revealed grain, complexity and structure. Galileo pointed his small tube at the Milky Way and saw that its milky band was made of uncountably many tiny stars, but there's no record that he turned that first telescope toward Andromeda's cloud. It would be another observer, working just a few years later, who would be credited, controversially, with the first telescopic look at what we now call M31. In 1612, the German astronomer Simon Marius claimed to have seen through his instrument a certain obscure spot in Andromeda's place which, through magnification, did not break into distinct stars but appeared as a bright centre fading toward the edges, like a candle seen through fog. He compared its appearance to a distant, unresolved blaze and noted that it remained fixed relative to the surrounding pattern. Whether he truly was the first or merely the first whose record survived, his description planted a seed. Such fuzzy objects were different from the pinpoints that dominated the catalogues. Andromeda's patch, when examined by observers like the Polish astronomer Johannes Hevelius in the 17th century and others who followed, maintained its dual identity, a hazy centre and an extended oval form, behaving neither exactly like a comet, which would drift against the stellar background, nor like a mere optical blur. It was bright enough to make its way into catalogue after catalogue, yet it did not fit neatly into any theoretical box. By the 18th century, systematic listing had taken hold. The French comet hunter Charles Messier, frustrated at confusing permanent smudges with the fleeting comet tails he pursued, set out to record these non-cometary nebulae so future observers could avoid them. His famous catalogue, begun in the 1770s, assigned Andromeda's cloud the designation M31, the 31st such object on his list, and he noted its brightness and shape from the rooftop of his Paris observatory, using a modest telescope compared to the giant mirrors that would follow, but still enough to show a luminous core stretching into an oblong halo. To him, as to most of his contemporaries, its nature was a puzzle only in the sense that all nebulae were. Their origin and constitution were matters of speculation, but the dominant assumption was that the universe consisted of the Milky Way, and whatever clouds and clusters lay inside it. In that same 18th century, though, philosophers of the sky began to imagine more daring possibilities. In 1755, the young Immanuel Kant, before he became famous as a philosopher of reason and morality, published a treatise on the structure of the heavens in which he proposed that some of the faint fuzzy nebulae might be island universes, vast collections of stars similar to the Milky Way but lying far beyond it, inspired partly by the Englishman Thomas Wright of Durham, who had earlier speculated that the Milky Way. Herschel's own view shifted over time. At first he favoured the idea that some nebulae were distant star systems, but later he became convinced that most nebulous objects were clouds of luminous fluid that might condense into stars. He observed Andromeda repeatedly, noting its bright core and extended form, but even with his considerable instruments it remained stubbornly unresolved into individual points, seeming rather like a unique specimen among the nebulous family, larger and brighter than most, perhaps closer or intrinsically more luminous, but still of uncertain breed. The middle of the 19th century brought a critical shift, the rise of astrophotography, which allowed the sky not only to be seen but also to be kept, examined and compared at leisure. In 1887, the Welsh-born engineer turned astronomer Isaac Roberts used a reflecting telescope and long photographic exposures to capture images of Andromeda that, when developed, astonished the scientific world. The plates revealed not merely an oval glow but a richly structured object, with discernible spiral arms wrapping around a bright nucleus, faint at the eye's eyepiece but drawn out by the camera's patience. For the first time, the Andromeda Nebula clearly displayed a spiral form like that of certain other nebulae already known, such as those in Canis Venatici and Virgo, and Roberts's photographs were widely circulated, fueling arguments about what such spirals could be. To some, they were still condensing clouds. Despite these hints that spiral nebulae might be enormous star systems far beyond our own, the astronomical community in the early 20th century remained split. Many believed that the Milky Way was the entire universe, stretching perhaps hundreds of thousands of light-years across, with nebulae as its internal constituents, while others, recalling Kant's island universes, argued that the spirals represented galaxies, though the term had not yet taken its modern meaning, that lay at distances so vast as to dwarf even the Milky Way. This dispute came to a head in 1920 in Washington, D.C., at what would later be called the Great Debate, a public discussion between Harlow Shapley, who championed a large Milky Way that contained the nebulae, and Heber Curtis, who argued that spiral nebulae like Andromeda were separate stellar systems. Curtis pointed to observations of novae, sudden stellar explosions, seen in Andromeda, arguing that if they were similar in intrinsic brightness to novae in our own galaxy, then Andromeda must lie far beyond the Milky Way to appear so faint. Shapley countered with his own measures of the Milky Way's size and brightness distribution, suggesting that our galaxy was vast enough to accommodate the spirals within it. These pulsating stars, whose brightness rises and falls with remarkable regularity, had been studied by Henrietta Swan Leavitt at the Harvard College Observatory, where she discovered that their periods, the time it takes for one full cycle of brightening and dimming, correlate closely with their intrinsic luminosities. Longer periods mean brighter stars. This period-luminosity relationship turned Cepheids into cosmic yardsticks. By measuring a Cepheid's period and apparent brightness, one could infer its distance. In 1923, Hubble examined a plate of the Andromeda Nebula and noticed a particular star that had changed brightness between exposures. He marked it with a tiny N for nova. Then, upon comparing additional plates, realized that the object's brightness fluctuated periodically rather than flaring once. He crossed out the N and wrote VAR variable. Over the following months, he identified more such variables in Andromeda, measured their periods, and applying Leavitt's relation, calculated their distances. The numbers he obtained were staggering. They placed Andromeda well beyond even Shapley's expansive model of the Milky Way, at more than 800,000 light-years away by his initial estimate. Later refined long-exposure photographs reveal that its stellar disk stretches roughly 200,000 light-years from end to end, making it, by most measures, somewhat larger in extent than the Milky Way's disk, and its total population of stars is often estimated at around 1 trillion, perhaps 2 or 3 times the number in our own galaxy, though such counts remain approximate, inferred from its luminosity and models of stellar populations. Viewed through instruments sensitive to different wavelengths, Andromeda's personality changes. In the ultraviolet, its spiral arms blaze with the hot, short-lived stars that have formed relatively recently, tracing out ring-like structures at particular radii where gas and dust have compressed into vast molecular clouds. In the infrared, observed by satellites such as Spitzer and the earlier eras, the galaxy's dust warms and glows, revealing a system of concentric, somewhat off-center, rings of star-forming material, one strikingly located about 10,000 light-years from the nucleus, another broader ring farther out, suggesting that gravitational interactions, perhaps with its small companion galaxy M32, have jostled, yet compared to the ravenous quasars seen at great cosmological distances, where black holes billions of solar masses in size gorge on infalling gas and outshine entire galaxies, Andromeda's central monster is relatively quiescent, accreting matter at a low rate and emitting only modest amounts of high-energy radiation. It is in effect a retired quasar, the fossil of a more violent youth, its current faintness a hint that Andromeda, like the Milky Way, has passed the most tumultuous stages of its active galactic nucleus phase and settled into a quieter middle age. Surrounding the bright hub and thin disk, Andromeda is encased in a vast, diffuse halo of stars, globular clusters, and dark matter that extends hundreds of thousands of light-years into space. The globular clusters in particular form a glittering retinue, compact spherical swarms of hundreds of thousands to millions of old stars, many more ancient than the Sun, bound tightly by their own self-gravity and orbiting the galaxy like bees around a hive. Early studies in the 20th century catalogued a few hundred such clusters. More recent surveys, benefiting from deeper imaging and better image processing, have pushed the count to over 500 confirmed members, with candidates numbering perhaps. Comparative studies of their halos show that Andromeda's outer reaches are more massive and metal-rich, containing a higher proportion of heavier elements synthesized in previous generations of stars, which in turn implies that it has undergone more frequent or more massive mergers with substantial companions. Models suggest that roughly 2 billion years ago, Andromeda may have experienced a significant merger that puffed up its disk and triggered a wave of star formation, leaving behind a younger halo component and heating some of its stars into more eccentric, thicker orbits. This relatively recent upheaval stands in contrast to the Milky Way's quieter recent history, though our own galaxy too bears scars of past collisions, such as the Gaia Sausage Enceladus event, inferred from streams of stars with distinctive orbital and chemical properties. Close by Andromeda's luminous disk, two easily visible companions swing in its gravitational grip, the dwarf elliptical galaxies M32 and M110. M32, a compact high-surface brightness object nestled just south of Andromeda's core from our perspective, is thought to be the stripped-down remnant of a once larger galaxy, whose his work, largely overlooked at the time, foreshadowed the more famous studies of Vera Rubin and Kent Ford in the 1970s, who carefully mapped rotation curves of Andromeda and other spirals with better instruments, and showed that the orbital velocities of stars and gas remained roughly constant, or flat, far out into the galaxy's outskirts, rather than decreasing as the inverse square law would predict if only the visible mass were present. This discrepancy between expected and observed rotation implied that Andromeda, like other galaxies, must be embedded in a vast halo of unseen matter, extending far beyond the luminous disk, containing several times as much mass as all the stars combined. Dark matter, the name given to this elusive component, does not emit, absorb, or scatter light in any appreciable way, but it reveals itself gravitationally, shaping orbits, bending the paths of light from distant objects through gravitational lensing, and influencing the growth of cosmic structures over billions of years. Estimates place Andromeda's total dark matter halo mass in the range of 1 to perhaps 1.5 trillion solar masses, comparable to or somewhat larger than the Milky Way's halo, though one plausible explanation is that one of Andromeda's satellites, perhaps M32, plunged through the disk along a path that perturbed the gas and set up expanding density waves, like the ripples emitted when a stone is thrown into a pond. As these waves travelled outward, they compressed the gas and triggered bursts of star formation along their crests, leaving behind a ring-like distribution of young, massive stars whose ultraviolet light outlines the pattern. Simulations of such encounters can reproduce the ring's general morphology and timing, suggesting that Andromeda's current face is, in part, the frozen echo of a relatively recent collision on cosmological timescales. Despite this activity, Andromeda as a whole is not an especially vigorous star-forming galaxy compared to blue, gas-rich spirals in the distant universe. Its global star formation rate is estimated at about 1 solar mass per year, give or take a factor of 2, somewhat comparable to the Milky Way's current pace. It contains large reservoirs of neutral hydrogen gas, mapped via radio observations of the 21-centimetre line, as well as molecular gas traced by carbon monoxide emissions, especially concentrated in its spiral arms and rings. But much of its gas has already been consumed or heated to temperatures where it is less efficient at forming new stars. In many respects, Andromeda and the Milky Way are both transitioning from the more exuberant, star-bursting, youth characteristic of earlier cosmic epochs into a quieter, more sedate maturity, gradually depleting their gas supplies and shifting their stellar demographics toward older populations. Radio telescopes, scanning the sky at wavelengths far longer than visible light, have revealed that Andromeda's neutral atomic hydrogen disk extends well beyond the bright optical disk, warped and twisted in its outer reaches, likely by the gravitational tugs from satellites and by past accretion events. This warped extended gas disk plays an important role in future evolution, as interactions and instabilities can funnel gas inward to feed star formation, or potentially a reawakening of the central black hole. In addition, Andromeda hosts a network of non-thermal radio emissions produced by cosmic rays spiraling around magnetic field lines, giving insight into the galaxy's magnetic structure and the interplay between supernova, charged particles, and interstellar fields. At shorter wavelengths, X-ray observatories like Chandra and XMM Newton have catalogued hundreds of discrete X-ray sources sprinkled across Andromeda's bulge and disk, including accreting binary systems where a neutral supernova remnants, the expanding shock waves from past stellar explosions, also shine in X-rays as they plough into the surrounding medium, compressing and heating it. By mapping these remnants, astronomers trace the galaxy's recent history of massive star death. The central region, though relatively faint in X-rays compared to active galactic nuclei, still contributes a diffuse glow from hot gas and unresolved point sources, reminding us that even a seemingly quiet galaxy hums with high-energy processes. Andromeda's solitary supernova of record, the 1885 event S Andromedae, left behind an interesting relic. More than a century after its light faded from human view, ultraviolet and optical spectroscopic studies of Andromeda's nucleus detected a circular patch of absorption features associated with iron and calcium, interpreted as the expanding shell of the supernova remnant silhouetted against the bright background of the bulge. This unusual way of seeing a supernova remnant, not in emission as with most galactic remnants, but in absorption against a dense field of stars, offered a rare chance to study the chemical yields and expansion of a Type Ia explosion in a relative. Andromeda, by contrast, is an outlier. Its spectrum is blue-shifted, indicating that, within the gravitationally bound environment of the local group, the mutual attraction between massive galaxies overcomes cosmic expansion. Its line of sight, or radial velocity toward the Milky Way, is about 110 km per second when corrected for the Sun's motion around the galactic centre, and for decades the transverse, or sideways, component of its motion remained largely unknown, leaving uncertainty about whether it would eventually collide with, merely graze, or perhaps orbit around our galaxy. In 2012, a team led by Roland van der Marel used Hubble Space Telescope observations taken over several years to measure Andromeda's tiny proper motion on the sky, fractions of a millionth second per year, the angular equivalent of watching a coin move a few centimeters at the distance of the Moon, and combined these data with radial velocity measurements to reconstruct its three-dimensional trajectory. Their results indicated that Andromeda and the Milky Way are on a nearly head-on course, with a predicted first close approach in about 4 billion years and a likely full merger into a single larger galaxy some 2 billion years after that, barring significant perturbations from other local group members. In this future cosmic rendezvous, the elegant spiral structures of both galaxies will be distorted, stretched, and eventually shredded by gravitation. Yet before this distant future, Andromeda has already played a crucial role in our understanding of how galaxies form and evolve over cosmic time. Its relative proximity has made it a prime target for detailed stellar population studies. Using the sharp eyes of the Hubble Space Telescope, projects like PHAT, the Panchromatic Hubble Andromeda Treasury, have resolved over 100 million individual stars across a significant swath of its disk, measuring their colours and luminosities in multiple filters to construct colour magnitude diagrams that reveal their ages and metallicities. By comparing these observations to theoretical isochrones, curves representing populations of stars formed at the same time, astronomers reconstruct the star formation history in different regions of Andromeda, mapping when and where bursts of starbirth occurred, when star formation waned, and how these patterns correlate with spiral arms, rings, and interactions with satellites. These detailed maps show, for example, that the 10 kiloparsec ring has been a favoured site of star formation for the past several hundred million years, with episodic enhancements possibly linked to passages of satellites or to the dynamics of spiral density waves. The inner disk, close to the bulge, appears to have experienced a more continuous, though gradually declining, star formation rate. Weak gravitational lensing studies, for instance, use the subtle distortions in the shapes of background galaxies seen through Andromeda's extended halo to infer the distribution of dark matter and test models of its clumpiness. Although such effects are more dramatic in massive clusters of galaxies, where strong lensing creates multiple images and arcs, even a single galaxy like Andromeda can warp spacetime enough to leave a statistical imprint when large samples of background sources are available. Combining these lensing measurements with dynamical data from satellite motions and rotation curves allows astronomers to refine their understanding of how dark matter is distributed within and around galaxies. If we could sit in a time machine and roll back the cosmic clock, we would see Andromeda not as the grand spiral it is today, but as a smaller, more irregular collection of gas and stars assembling in the young universe. Galaxies like Andromeda are thought to have formed hierarchically, building up from smaller progenitors that merged and accreted over billions of years. In the first billion years after the Big Bang, the cosmos was populated by protogalactic fragments and primordial gas, within which the first generations of stars, massive metal-free population 3 objects, ignited and quickly died, seeding their surroundings with heavier elements. As these fragments coalesced, Andromeda's early core would have taken shape, its initial stars blazing blue-white and producing intense ultraviolet radiation that contributed to the reionization of the intergalactic medium. Over time, cold gas streams flowing along cosmic filaments fed the growing galaxy, while successive mergers with other forming systems both increased its mass and stirred its structure, sometimes triggering starbursts and sometimes heating and thickening its disk. The thick disk and classical bulge observed today may be relics of this violent early era, when collisions were common and massive. As the universe aged and structure formation decelerated, mergers became less frequent and less catastrophic, with minor accretions of dwarfs and the slow infall of gas shaping the more quiescent evolution of the last several billion years. Simulations that model such hierarchical growth under the influence of dark matter and cosmic expansion, when tuned to reproduce Andromeda's current properties, its mass, rotation, satellite system, and halo substructures, offer plausible historical narratives that merge the galaxy's observed past with cosmological theory. In threading this story from subtle little cloud in a medieval manuscript of future sky-filling partner in a galactic union, we return, finally, to the perspective of that faint smear in Andromeda's place, which once fueled myths of chained princesses and monstrous sea beasts, now carries, encoded in its photons, the record of 2.5 million years of travel through nearly empty space, approaching us not as an omen or a sign, but as a messenger from an independent realm of suns whose recognition transformed our sense of cosmic citizenship. Every improvement in our instruments, each larger mirror, each new detector, each sensitive spectrograph, radio array, X-ray observatory and space telescope, has peeled back another layer of its complexity, revealing a structure at once familiar and strange, a spiral cousin to our home, yet with its own black hole's mass, its own scarred halo, its own retinue of satellites, its own history of violence and calm written in tides and streams and rings of young stars. As we continue to refine our measurements to map its stars with ever finer precision, to chart its dark matter with more subtle traces, to anticipate the long dance that will eventually lead it into our arms, Andromeda stands as both object and symbol, proof that the universe extends far beyond the border of the Milky Way, testimony that the apparent stillness of the sky hides motions on scales so vast that only patient generations of observers can discern them. This act of classification might at first seem like an exercise in cosmic taxonomy, but by assigning Andromeda a specific place on the tuning fork, Hubble implicitly tied its appearance to its physical properties, its distribution of mass, its angular momentum, its history of star formation and mergers, and provided a framework in which it could be compared with more distant spirals that could not be resolved in as much detail. As telescopes improved, that initial label was refined. Some authors called it SASB, others SBAS, EAS2, in the language of Gérard de Vaucouleurs' more intricate system. But the broad picture remained. Andromeda exemplified a massive, luminous, relatively early-type spiral, a near archetype of its class, and a standard against which more remote galaxies could be judged, especially before instrumentation allowed those far-off systems to be probed with the same granularity. Hubble's own work on the velocity-distance relation, which would become the Hubble-Lemaitre law, did not rely on Andromeda directly, since its peculiar motion within the local group, a headlong approach instead of recession, made it an outlier to the trend. But the very fact that its distance could be determined by Cepheids helped calibrate the first rung of the extragalactic distance ladder on which that relation rested. Cepheids in Andromeda served as stepping stones to brighter standard candles in more remote galaxies, and those in turn anchored the slope of the expansion law. Thus, even though Andromeda itself did not lie along the smooth recessional flow, it quietly underpinned the numerical scale by which the universe's expansion would be measured, much as a local yardstick, never leaving a workshop, determines the dimensions of ships that sail the open ocean. Once the existence of multiple galaxies was accepted, attention turned increasingly to the structures and populations within Andromeda that could not be seen, even in principle, in far more distant spirals. One of the most revealing probes of its oldest constituents came from a different kind of variable star. The R. Lyrae pulsators, low-mass, horizontal branch stars that vibrate with short periods of less than a day and relatively uniform intrinsic brightness. These variables inhabit globular clusters and the extended halos of galaxies, and their detection in Andromeda's outer regions provided a direct signpost of an ancient stellar population, one that formed more than 10 billion years ago. By measuring RR Lyrae in the sparse star fields far from Andromeda's bright disk, astronomers confirmed that its halo, like the Milky Way's, was built around a population of very old metal-poor stars, relics of the galaxy's earliest. By dispersing their light and examining the strengths of absorption lines from elements like iron, magnesium and calcium, observers could infer the metallicities of individual stars and construct a metallicity distribution function for various regions around the galaxy. These studies showed that Andromeda's inner halo is, on average, more metal-rich than the Milky Way's, suggesting a history in which Andromeda experienced more substantial mergers with relatively enriched satellites, or perhaps formed more of its halo in situ through early intense star formation. Further out, the metallicity drops and the distribution broadens, pointing to a mix of accreted fragments, each with its own chemical fingerprint, overlapping along our line of sight. In this way, Andromeda's halo becomes not a monotone backdrop but a mosaic, each tile representing a separate ancestral system, long since unbound. One of the most startling revelations about its outskirts arrived when careful mapping of its fainter companions revealed not just isolated dwarfs sprinkled randomly around it, but a striking planar arrangement of many of those satellites. Using deep imaging from the Pan-Andromeda Archaeological Survey, an international team led by Rodrigo Ibata and others in the early 2010s found that a significant fraction of Andromeda's dwarf M33 is a smaller, less massive spiral than Andromeda, with loosely wound arms and vigorous star formation in bright H2 regions like NGC 604, and for much of the 20th century, its dynamical relationship to Andromeda remained uncertain. Was it a satellite bound to its giant neighbour, an independent member circling the local group's barycenter, or a passing interloper? Precision measurements of M33's proper motion using very long baseline radio interferometry, tracking compact Mesta sources in its star-forming regions, suggested that it is indeed moving in a manner consistent with being gravitationally tethered to Andromeda, though perhaps on a long, eccentric orbit that has not yet carried it into a close encounter. Subtle warps in M33's gas disk, asymmetric star formation patterns, and tantalizing hints of tidal features between M33 and Andromeda in deep imaging all point to at least one past interaction between the two, perhaps a close past that stirred both disks and helped sculpt Andromeda's outer rings. By modelling these possible encounters, astronomers not only reconstruct the individual orbits of galaxies, but also estimate the total mass of Andromeda's halo, since only a sufficiently massive host could have so strongly influenced a sizable companion like M33. In this inferential game, positions and velocities become test particles, tracing an invisible gravitational landscape in which Andromeda plays the central role. If the motions of stars and satellites sketch the mass distribution, other more elusive components of Andromeda announce themselves in how they intercept the light of even more distant beacons. The circumgalactic medium, a vast reservoir of tenuous ionized gas enveloping the galaxy far beyond its luminous disk, cannot be seen directly in emission over most of its extent, yet it leaves narrow absorption lines in the spectra of bright background quasars whose sight lines pierce the halo. Using the cosmic origin spectrograph aboard the Hubble Space Telescope, observers have identified multiple such quasar beams passing near Andromeda on the sky, and measured the fingerprints of highly ionized oxygen, silicon, and other elements in their spectra, revealing that Andromeda is surrounded by a massive metal-enriched atmosphere extending out to, and perhaps beyond, its virial radius. Analyses of these absorption systems indicate that the mass of this hot, diffuse gas may rival. In such studies, Andromeda ceases to be an isolated island and becomes a key node in a larger network of baryons cycling between galaxies and their surroundings, a laboratory for testing ideas about how matter circulates on scales hundreds of thousands of light-years wide. While ultraviolet spectrographs trace the invisible gas, infrared and submillimeter instruments reveal the cold dust threaded through Andromeda's disk, dust that both obscures and reprocesses stellar light. The Herschel Space Observatory, with its PAX and SPIRE instruments, mapped Andromeda at wavelengths from 70 to 500 microns, detecting emission from grains warm to mere tens of degrees above absolute zero. These observations show that the dust is not distributed smoothly. Instead, it forms complex filaments and rings that echo the star-forming structures seen in shorter wavelength data, but also expose regions where past episodes of star formation have heated and eroded the interstellar medium. By fitting models of dust emission to the Herschel data, astronomers estimated the total dust mass of Andromeda and derived dust-to-gas ratios as a function of radius, finding that, as in many spirals, dust abundance declines with distance from the centre, tracking the metallicity gradient. The coldest dust resides primarily in the outer rings and arms, where lower radiation fields allow grains to remain frigid, while warmer dust near the core glows more brightly at shorter infrared wavelengths. These variations, when combined with CO&HI maps, permit a detailed test of theories linking gas surface density, dust shielding, and star formation efficiency, turning Andromeda into a proving ground for the empirically derived Kennicutt-Schmidt law that relates gas content to the rate at which new stars are born. High-energy observations extended the picture in the opposite direction, into the realm of gamma rays, where only the most extreme processes leave a mark. The Fermi Gamma Ray Space Telescope, surveying the sky in photon energies from tens of MeV to hundreds of GeV, eventually detected closer to the galaxy's heart, X-ray imaging uncovered a handful of unusually bright point sources, so-called ultra-luminous X-ray sources, whose luminosities exceed the Eddington limit for typical stellar mass black holes, accreting hydrogen-rich material. Although Andromeda's ULXs are relatively modest compared to some in starburst galaxies, they nonetheless raise questions about whether they harbour intermediate mass black holes, or whether geometric beaming and super-Eddington accretion can explain their output. Monitoring campaigns with Chandra and XMM Newton track their variability, searching for quasi-periodic oscillations and spectral state changes indicative of the accretion physics at work, and through these systems, Andromeda's outskirts become, paradoxically, windows into the behaviour of gravity and radiation in the strongest fields short of galactic nuclei. In the calmer reaches of the disk, planetary nebulae, expanding shells of gas ejected by dying low and intermediate mass stars, serve as yet another set of traces of Andromeda's structure and dynamics. Their bright emission lines, particularly the greenish O3 line, at 5007 angstroms, stand out sharply against the background of unresolved starlight, allowing observers to catalogue thousands of planetary nebulae across the galaxy and measure their radial velocities with high precision. By plotting these velocities against position, in the 1990s and 2000s, projects like Pointergape, WeCap and MEGA used wide-field cameras to monitor Andromeda's central regions nightly, searching for the telltale symmetric light curves of microlensing events superimposed on the noisy flicker of intrinsic stellar variability. Unlike similar surveys toward the Milky Way's bulge, where individual stars can often be resolved, Andromeda's greater distance means that each pixel on the detector contains light from many stars, so lensing manifests as small fluctuations in the total pixel brightness, a technique dubbed pixel lensing. Despite this challenge, multiple candidate events were detected, some attributable to lensing by stars in Andromeda's own disk and bulge, others potentially caused by more exotic lenses in the galaxy's halo. By comparing the observed event rate and properties with theoretical predictions, researchers placed constraints on the fraction of Andromeda's dark halo that could be made of compact objects such as primordial black holes or faint non-luminous stars, MACOs, or massive compact halo objects, helping to rule out certain models of dark matter composition on galactic scales. Meanwhile, the globular cluster system, long recognized as a rich component of Andromeda's outskirts, yielded new surprises when examined with deeper imaging and multi-object spectrum. The presence of such youthful stars in the immediate vicinity of a massive black hole raised questions about how star formation could proceed in such a hostile environment, where tidal forces and energetic feedback would seem inimical to the collapse of gas clouds. Theories propose that gas driven inward by bar-like instabilities or minor mergers could settle into a dense disk around the black hole, fragment, and form stars in situ, despite the extreme conditions, leading to a recurrent cycle of nuclear starbursts that build up the central cluster over time. On larger scales within the disk, subtle non-axis emetric features hinted that Andromeda might host a bar, a linear arrangement of stars and gas extending from the centre and driving angular momentum redistribution through gravitational torques. Infrared photometry and dynamical modelling suggested the presence of such a bar, oriented at a particular angle relative to our line of sight, with its ends perhaps connecting to the inner spiral arms. Bars can channel gas inward, fueling central star formation and black hole accretion, and can also reshape the orbits of stars in the disk, contributing to the thickening and radial mixing of stellar populations. If Andromeda indeed harbours a bar, its properties offer clues to the secular evolution that has gradually transformed the galaxy's inner regions over billions of years, superimposed on the more stochastic effects of mergers and interactions. Even the thickness of Andromeda's stellar disk encodes information about its past. Spectroscopic surveys along slits and integral field units across the galaxy have measured how stellar velocity dispersion and scale height vary with radius, revealing the presence of a distinct thick disk component populated by older, kinematically hotter stars that orbit with somewhat lower rotational speed than the younger, thin disk stars. The relative mass and chemical properties of this thick disk, richer in alpha elements produced by core collapse supernovae, poorer in iron peak elements generated in type Ia supernovae, offer a timeline of early disk formation and subsequent enrichment, suggesting that Andromeda's disk may have been dynamically heated by early minor mergers, or by internal processes like scattering off giant molecular clouds, imprinting a vertical structure that differs subtly from the Milky Way's. Beyond the realm of professional observatories, Andromeda has also become a touchstone for generations of amateur astronomers and astrophotographers, their evolving depictions of it paralleling the advancement of technology available to non-professionals. In the digital age, with sensitive CCD and CMOS sensors, narrowband filters, and sophisticated image processing accessible to backyard observers, Andromeda's portrait has been rendered in ever more exquisite detail from suburban backyards and mountain ridges alike, revealing not only its main body but also faint outer rings, tidal plumes, and tiny satellite smudges that once required the largest professional telescopes to discern. These amateur datasets, while primarily created for aesthetic pleasure, occasionally contribute scientific value as well, providing long baseline monitoring of variable stars and transient phenomena that can supplement professional surveys. Citizen science projects invite volunteers to comb through Andromeda images and light curves, classifying variables, identifying potential microlensing events, and flagging unusual sources, multiplying the eyes trained on the galaxy by thousands. In this sense, Andromeda serves not only as an object of study, but as an entryway into the practice of astronomy for countless enthusiasts. Its soft glow, a shared reference point across cultures and generations. In the realm of speculation, Andromeda invites one more question that hovers at the boundary between science and imagination. If it hosts on the order of 1 trillion stars, many of them similar, we cannot know whether such minds exist. Yet the mere possibility reframes Andromeda not only as an astrophysical object, but also as a potential host of narratives, histories, and perceptions as rich and layered as those we have spun about it. Its transformation, in our understanding, from a mythic backdrop to a gravitational partner, and eventually to a key testbed for cosmological theories, reflects our own growth as observers and thinkers, and as new generations of telescopes, extremely large mirrors on the ground, more sensitive arrays in space, prepare to scrutinize its stars with even finer precision, searching for the spectral whispers of individual supernova progenitors, the minute wobble of binary companions, and the faintest glimmers of its most distant halo members. Andromeda waits in the sky, unchanged in its slow rotation, while our questions, like the beams of our instruments, grow ever more finely focused.